Okay, oh, this looks good. Oh, and the share video too as well. All right. Oh, and you should be able to see not just through the video, but the screen share. Let's see. Everything has changed. What's up, everyone? Oh, there we go, entire screen. Okay. Okay, Matt, you should be able to see our screen as well, and I am recording this, so you'll have to skip ahead 5 minutes to get to the real lecture. All right, so I am going to do yet another quick review of the stuff that we covered in the first two classes of GLMs and logistic regression, but we're going to focus today on fitting and interpreting the interaction terms, and I'm going to introduce this interesting thing called the model matrix, which gives you a lot of flexibility in how you fit your generalized linear models. Recalling our components of the GLM, there are the three of them. The random component, which specifies your distribution of the response variable conditionally on any particular set of values for the predictor variables. Does that make sense to everyone, that conditional distribution? It's a little bit of a statistical sounding word, but it means something pretty intuitive. It means the conditional distribution. You remember how I was talking about how the residuals, like in a linear model, the residuals are assumed to be normally distributed, but not necessarily the y values themselves, but the residuals. So the distribution of the y variable itself is just its so-called marginal distribution, or it's just overall distribution averaged across all of the values of the predictors. The conditional distribution means it's the distribution conditional on one particular set of values of the predictors. So, and that's what has to be in a linear model normally distributed. So for a given value of x, the distribution of y is going to be assumed to be a normal distribution with mean 0 and a fixed standard deviation. So that's just another way of saying that we're talking about residuals here, about what's left over given a certain value of the predictors so what the model has predicted. So in the linear model, those had to be normal. In a GLM, they don't have to be normal. There's an entire family of distributions that they can belong to. The systematic component is this linear function, a set of coefficients that are multiplied by the predictors and then added together. And this is the same for the entire family of generalized linear models. That systematic component is always the same, or the same idea, that it's a linear set. It's the linear predictor, it's called. And the final component is this link, which is applied to the expected value, that left-hand side, and we denote it here by the function g, and that's your relationship between the expected value of the random component and what is predicted by the systematic component. So you have your random distribution of y's for any given value of your x's, it has an expected value. You put that through the function g to relate that to the linear predictor. So these are the three components of all generalized linear models. In logistic regression, the random component is a binomial distribution. So the y variable is binary. In a given sample, those binary values are assumed to be independent. So they are a, what's that trial called? When you have, what's that? Bernoulli distribution, or it's a Bernoulli trial, and the probability distribution is a binomial distribution. So for a fixed set of the predictors, any observations in your study have the same predicted or expected probability of your outcome, and the distribution of outcomes for that particular probability is a binomial distribution resulting from a Bernoulli trial. Getting in lots of stats words so far today. The systematic component, of course, always the same, the linear predictor. And in this case, for logistic regression, the link function is a logit function. So, which is the log odds for the event relative to, well, the prediction is just the log odds for the event. So writing this out, G is the logit, so the logit of the probability of your event. So that's the expected probability of a 1. If we're talking about the 0-1 coding, is which is the log of probability over 1 minus probability. That's that is the logit function, or the log odds, is equal to the linear predictor. So just switching it around, the probability of an event, if you're predicting that for any individual in this study based on your model, is the inverse logit of your linear predictor. Linear regression is an additive model, meaning that the contributions from each one of the variables, or the contribution from an increase in one of the variables, are added to your expected value. Remember, I promised I promised my colleagues that at the end of this course, no one here will be confused about which of the models you use are additive and which ones are multiplicative, because it really matters in how you interpret the coefficients. So if you have two binary variables with coefficients of 1.5, so say this is we're fitting a model to the probability of completing your degree, and we have predictors for whether the student is having to work while going to school, and for whether the student is full-time or part-time, then if our baseline group is not working and full-time student, then for the alternative categories of working and part-time student, those would each add 1.5 to the log odds. So they would, sorry, I'm getting ahead of myself. I was just talking about a logistic regression, right? Not a linear regression. So in that case, the outcome is not whether they complete, but let's say the outcome is GPA. So it's kind of bounded, but at least it's a continuous variable. It's going to add 3 to the GPA. Not very realistic, but the point is that they add. Whereas in logistic regression, So if we're talking about completion of the program, it adds 3 to the logit of the probability. So the logit of the odds. And this odds then increases by e to the 3, which is about 20-fold. I'm worried nobody interrupted me when I started talking about the first one as a logistic model. You're just being polite? Okay. Going back to that motivating example of contraceptive use, remember we had 3 predictive variables and we had an outcome variable. The outcome was whether the individual is using contraceptives, and the 3 predictors are their age, education level, high or low, and whether they respond that they want more children. And just fitting a simple univariate logistic regression model to this, I'm just taking the one that is probably going to be the strongest predictor of contraceptive use, whether they want more children. I plug this into the GLM function using, remember this kind of funny cbind method where I just binded together these 2 columns. It's a shortcut for having to create a really long, skinny data frame with wants more as the predictor. Specify the data set, which I called Qs. You can look in the lecture notes for the command in the RMD file itself for the command that loaded the Qs data set from the internet. And I specified under family that I wanted a binomial error model with the logit link function. With some hidden code, I produced this formatted HTML table here that has the coefficient estimates, their standard errors, their z-values, and then the probability of a z-value greater than this based on the Wald test. So I need some help in interpreting this table. We have an estimate of minus 0.18 for the intercept. What does that mean? I could scroll down and show you, but I won't. Some brave person.
A 1 unit increase in the variant to minus 0.18 for decrease in the predictor.
So okay, a 1 unit increase in the predictor. What does that mean? What's a 1 unit increase in the predictor? The predictor is whether or not the individual wants more children. Okay, you can jump in.
Okay. Minus 1.0486 is the log odds.
Wait, we're still on intercept.
Okay. Oh, intercept. Okay.
Yeah, what's the intercept? What's that minus 0.18 mean?
The starting point, like we're assuming that right off the bat, most people, right, since most people are not using contraception. Is that what that means, right? Because our predictor variable is if they want more, and then the outcome variable is if they're using or not using contraception, right? And so the intercept, which is like where basically that's where we begin to see data, right? Is at this point.
Yeah. Yeah.
So we begin to see data at the point like the starting point is that people are like, and this is like, you have to convert this, or you have to exponentiate this, right? Does that make sense of it?
Yeah.
But it looks negative, so it looks, I mean, it looks like it's
You're making it more complicated though than it needs to be. I'm not quite following. It sounds like you're on the right track. Yes.
Isn't it just the null, the log odds of the probability of using contraception with the null model where you have no predictor in the model?
Close. So it is the log odds of contraceptive use. For whom? It is the log odds of contraceptive use for a group of people in our study, as predicted by the model. Yeah, it's for our reference group, and our reference group here, because I'm getting a hint from this, wants more yes. The reference group wants more no. So this is the log odds of using contraceptive for the group who does not want more children. So if you want the probability, you have to do that inverse logic function. And then you would actually get a probability. What can you tell by the fact that it's negative?
Under 1.
Well, probabilities are always under 1. Probabilities are always between 0 and 1. So that's true. Tell me something more about it. Yes.
It's a low probability.
It's a low probability. What's it lower than?
I'm sorry?
What is it lower than? You're right, it's a low probability.
Lower than 1?
It is lower than 1, but it's also, so it was on last, I didn't put it in again here, but do you remember I actually brought a little device here. I don't know if it's going to work. That's supposed to let me draw. I don't think it's actually going to.
It's lower than 0, right?
What's that?
It's lower than 0, right?
No, it's not lower than 0. You can't. Well, the log odds is lower than 0, but probability is always between 0 and 1. Okay, let's look at this function. This function, when the probability gets close to 0, p over 1 minus p is close to 0, and the logarithm of that is minus infinity. So a probability of 0 gives you a log odds of minus infinity. A probability of 1, this is 1 over 0, this goes to infinity. What about a probability of 0.5? What do you get here? This is the logit, or the log odds function. 0.5 over 1 minus 0.5, that's, I really want to be able to write. I'm going to try doing something a little bit different to allow myself to write. Yeah, I could just use our studio, that'll do. Okay, so I'll try to, just to remind myself, to remind you, this is the logit function. I'll go ahead and make a function, logit function of p over 1 minus p. So logit of 1, what did I say that was? Oh, come on, I just told you. Infinity, yes, infinity. Up, yeah. And the logit of 0, negative infinity. Wait, I put this in right. P over 1 minus P. Oh, tell me what did I do wrong here? Log, thank you. Log. Okay. There, now logit of 0 is minus infinity. Okay, I'll buy a coffee for whoever tells me what the result is here.
One.
Phew, no coffees. Okay, so it makes sense, right? That like the if the probability of something is 50%, say it's a coin flip, the probability of a heads is 50%. What are the odds of a heads? 1 and 2. Well, sorry, the risk is 1 and 2. The odds are 1 to 1. So the odds are 1, and the log of 1 is 0. So logit of 0.5 is 0. So a negative log odds.
It's 0.
Hmm?
It's 0?
Below 0.
No. What is a negative log odds? What does that say about the probability?
Oh.
Less than 0.5.
It's less than 0.5. Very good. Yeah. So let's see. Remember logit. Logit of 0 is minus infinity. Logit of 0.5 is 0. Logit of, let's say, 4 is something negative. So negative log odds mean a probability less than 0.5, less than even odds. So what if I had, let's take a look at, so what if I had, where are we? What if this were positive? What would that tell me about the probability of this group using contraceptives?
So over 0.5.
Yeah, it's more than 0.5. It's between 0.5 and 1. So someone tell me now in one concise sentence, what does this estimate of minus 0.18 mean for the intercept? Yep.
The odds, or okay, well, yeah, the odds of for those who do not want more children.
Yep.
The odds of their using contraception is less than 0.5.
Their probability is less than
Their
0.5. Their odds are less than even.
Okay, right.
Yeah.
Their probability is less than 0.5 and their odds.
Right. So the intercept always refers to the reference group. And so whatever your reference group is, even in a big multivariate model, your intercept will tell you what the expected value for the reference group is. Here, the reference group is everyone who does not want more children, and this tells you the log odds of that group using contraceptive. And it's something, the log odds is negative, the probability is something less than 0.5, but greater than 0. Okay, what about this estimate? Wants more, yes. What does this mean? I'll tell you what, I won't torture you. I made a figure here. So I've actually plotted the data here and given you a graphical representation of what these coefficients mean. So I've put wants more children, no, and yes. Added a little bit of jitter so that points don't end up on top of each other. And what I'm plotting on the y-axis here is the logit of the fraction who are using contraceptives. So this is from the actual data. So so we happen to have a fraction for each of those groups. That's why there's not just 2 points here. Remember, we have 4 different ages, 2 education levels, in addition to whether or not they want more children. So that should be 8 data points here, and I think it is. Here's the intercept. So first I put the y-axis at 0. So this is a 0 log odds, and the green is the intercept. And what this is just the average of these values in the reference group. So we have 8 values in the reference group. You can calculate the log odds for each one of them because you have the probability, right? All you would have to do, you could get this estimate by hand, even pretty easily. All you would have to do is looking at the actual data set for each one of these groups. You have the probability, which is using over using plus not using, and then calculate the odds and take the log. And then whatever the average of that is, that's your intercept. And then our coefficient for wants more yes is this red line, which is the difference in the average log odds between these 2 groups. So the intercept gives us the log odds for the reference group, and the coefficient gives us a difference in log odds for another group. And why is this additive? I told you, didn't I, that logistic regression was a multiplicative model, and now I'm confusing you. Why am I still saying it's a difference?
Because it's on the log scale.
It's on the log scale, right? And that's why I'm doing this on the log scale here, so that I can show it this way. On the log scale, everything is still additive. It's on the scale of probabilities that it's multiplicative. It's the scale of the actual outcome or y variable, it's multiplicative.
What about this as additive, though, at this stage?
What about this as
What about
additive?
this is, I'm saying, what about this in the graph? Or why are you
So
saying this is additive?
I'm saying it's additive because I'm saying the intercept, okay, is here, but the coefficient is the difference in these 2 averages, the difference in the average log odds of the reference group and the average log odds of the comparison group who wants more children.
So it's the difference between the estimate of negative 0.1864 and the negative 1.0486.
Well, okay, there's a good question. You've told me how to interpret the probability, or how to calculate the probability of the reference group who does not want more children, their probability of using contraception anyways. How would I calculate the probability of the comparison group who wants more children of using contraceptives? How could I get that from this table or from this graph?
Can you repeat the question?
Okay, my question is, what is the probability of the group who wants more children using contraceptives?
Less than 50%.
Sorry?
Less than 50%.
It is less than 50%.
Estimate is minus 1.18, so 1.04. It's
Let's see. So based on my on my intuition, I'm going to say here that the outcome is in fact not. Wait, the outcome. So we have a negative coefficient for the group who wants more children, which means their log odds is lower, their probability is lower. So my intuition is telling me that that's a lower probability of not using contraceptives. Am I right? Or am I just mixing myself up?
Using contraceptives.
Okay, so
less likely
of using contraceptives. So, right. So the coding here is that 1 is using contraceptives and 0 is not using contraceptives. And this is saying there is a lower probability in this group of using contraceptives relative to the comparison group who does not want more children. Okay, everything makes sense. I had a little bit of a hiccup there. But nobody answered my question still. How do I calculate the probability that the people who want more children are using contraceptives? Yeah.
So you said that the estimate for wants more is the difference in the two. So would you do the difference in those two estimates and then do the probability?
So what you're describing to me, this difference is the difference between the two groups. So if you take this difference, this is a log odds ratio, and if you exponentiate it, it will give you an odds ratio between the two groups. So that's a good answer, and that's often what you would want to do. But in this case, I'm asking just for the predicted absolute probability of this group using contraceptives.
Take the inverse logit of the sum.
Exactly. So you add them up and then take the inverse logit. And that's what you see in this plot here. Here's the intercept. So that's something small and negative. You add to that the coefficient, something larger and negative, and you get to the average log odds for the comparison group. And then when you do the inverse logit, it would turn that into a probability. So this is a nice, this is the simplest possible case. It's only a univariate analysis. We only have one coefficient, but this holds for multivariate analyses as well. If you have 10 different coefficients that you have fit, and we're going to do that. Well, here's just an intercept plus 3 coefficients that we fit if we use the age groups as predictors. So in this case, someone can only belong to one of these. They can either be in the reference category or in one of these other age groups. The estimate is the log odds for the reference group, which was under 25 years old. And the probability of using contraception increases for each increasing age group. What is this 1.0483? What is that a comparison to? Or how do you interpret this coefficient? Slightly more complicated than the last one, but it's exactly the same answer. Only slightly more complicated because we have 3 coefficients now. But the answer is not actually more complicated.
Which is the reference group?
Which is the reference group? Let's see. Less than 25. The reference group is the one that we don't see a coefficient for.
No, I know, but it wasn't written down.
Yeah. It never.
On this slide.
It never appears in the table of coefficients.
No, I meant underneath where you have the bullet point. I couldn't remember what it was. If it was
less than 25. So what's the 1.0483?
It's comparing it to the reference group.
Yeah. So that's the difference in log odds of probability of using contraception for 30 to 39-year-olds relative to those under 25. And so the reason I said it increases for each age group is not because that is directly in the table, but in my head I was saying, okay, 1.04 is bigger than 0.46, and 1.42 is bigger than both of those. So that log odds of, or the probability of using contraceptives is increasing for each older age group. Recall the model formula. This is a nice flexible interface that exists in every advanced statistical software package, I think, that provides a sort of a shortcut way for defining models. And we are going to cover a slightly more manual way today, but a lot of the times this is good enough. And the key things you need to remember are just adding including a variable, deleting it, including an interaction, including the main terms plus the interaction. Interaction is up to a certain order of interactions. You have 3 or more variables, and deleting an intercept, which you would probably very rarely want to do. Now it's getting actually a little bit more complicated. I've done a multivariate regression now with 2 different variables here, age and wants more children. So now I have an intercept. Again, I have 3 coefficients for age, but I also have one for wanting more children. So what's the reference group now? Yeah.
Under 25 and do not want more children.
Exactly. The reference group is those who are under 25 and do not want more children. And the log odds for that group of using contraceptive is -0.86, which means a probability certainly less than 0.5, greater than 0. Now, let's see, I asked you about how to interpret this age 30 to 39 coefficient before. I just want to show you back here. It was 1.0483, and now it's 0.8078. So it's actually changed, which is kind of interesting, right? Any guesses as to why it's changed or how we can interpret it? Yep.
Some of the variability in the previous model is now in wants more children. So because we added another variable to the model, it adjusted the value each of the other covariates had.
So it's true that some of the variability that before was just a part of the residuals is now being assigned to wanting more children, but variability is something that affects the standard error, the z-value, and the p-value, but variability is not the mean. This is just an average. The estimate is just an average.
But the fact that the groups are not wants more children, yes and no, is not equally split up among the 3 age groups.
Yes, that is a part of it. the thing here is that the reference group is changed here, and that the reference group is now those who are under 25 and who do not want more children. So, and this group is those who are 30 to 39 and do not want more children. So this is only a comparison between those who do not want more children. Yeah.
Wait, so I thought the estimates, they're like absolute. They're not. Are these relative to each other? Are we saying these values are relative to the reference group even at this stage before they're transformed?
Yes, I'm saying.
I thought you were saying that like you get a ratio that would be comparing to the reference group like the probability, but at this point this is the absolute probability of each age group sort of by themselves between 0 and 1, so it's not conditional on the other reference group. Right? If you can calculate the probability for each one of these groups in a simple, like without, it's a non-comparative probability, right? It's just like the probability of these.
Okay, so yeah, maybe a better way to say this is that, and the standard way of saying this is that this is the increase or the change in log odds of using contraceptive among 30 to 39-year-olds relative to the reference group, holding whether or not they want more children constant. So this would be a comparison in the reference group and a comparison in the other group averaged together. But the point that you made about this not being a balanced design is an important one, that there are different numbers of participants in each of these groups. If this was a perfectly balanced design that I need to check this now, but I believe that estimate would be the same. The standard error and the p-value would change, but not the estimate. So I can now, if I want to calculate the probability of those who do not want more children and are between ages 30 and 39 of using contraceptives, I again start with the estimate, with the intercept, and then add to that the coefficient for 30 to 39. And that will be for the group who does not want more children. If I want the probability of the group that does want more children and is between 30 and 39, I would start with the intercept, add this 0.80, and then subtract 0.82. So being older and wanting more children almost exactly cancels out the probability of wanting more children. And the other important part of this table for inference is, of course, going to be the column of p-values. And all of these are highly significant predictors. Or the first age group is not so significant. There's not that big of a difference in contraceptive usage from the under 25 group to between 25 and 29. The rest are all quite significant. If we want to know whether the effective age is modified by whether the woman wants more children or not, or you could think of it another way about whether the effect of wanting more children is modified by age, then you add this interaction term in the writing down of the model. It's a multiplication of these two values with its own coefficient. And in the model formula, it's also an asterisk. And looking at this, we have all of the same coefficients as we had before, but we now have these three interaction terms between wanting more children and the three comparison age groups, and an estimate for each of these. So now if you wanted to calculate the probability of someone 30 to 39 years old who wants more children, if you want to calculate the probability of someone in that group using contraceptives, you need to go through a few steps. You start with the intercept, add the main effect of age, add the main effect of wanting more children, and then add the intercept for those two. And so now we're seeing that actually the effect of wanting more children is not so big, but it's very large for the older age groups. So for those over 30 and over 40, whether you want more children has a very strong effect on contraceptive use. Or another way to put that, among the youngest groups, there's not such a big difference in rate of contraceptive use depending on whether they want children or not, but among the older women, especially over 40, it's a very big difference in the decision to use contraceptives. I promised I would introduce this design matrix to you. I'm probably not going to have to use it this semester, but you should know about it because it is accepted by any regression functions in R or SAS for that matter, and it is the most flexible way to define a model. When you have a certain study design or experimental design, there are any number of different models that are all correct that you could fit to it. And we've seen how with the model formula, by default, you're probably going to, for categorical variables, end up with alphabetical order, the group that comes first in the alphabet being a reference group. It's a totally arbitrary choice, but the software has to choose something, so that's what it does. You can change that using the re-level function to define what your base or your reference group is, but there are more possible models that you might want to consider that you need to use a design matrix for. What it is actually not that complicated. But I'm writing out here the matrix algebra formulation of linear regression. If this were a GLM, then these would be instead expected values, and there would be a link function here. But in this formulation, so this is just a simple linear regression. There's only one predictor. For every predictor you have a column in this matrix. So there's one column that's just ones. That's going to correspond to your intercept, and one column for each variable. And in this linear algebra formulation of the linear regression, you multiply your data by a vector of coefficients and add a vector of residuals to get your y values. So, I don't know if you remember how matrix multiplication goes, but it would be, so each row here is an observation. It would be 1 times beta plus x times beta 1. So that sounds just like your linear predictor, right? Plus epsilon 1 equals y1. So this is exactly like you learned But in this notation, you would then go and repeat. So for your second observation, 1 times the intercept plus the x variable for observation 2 times its slope, beta 1, plus epsilon 2, that residual is equal to y2. So all this does is each row here tells you what your systematic and residual components of y are according to your model. And in this formulation, the design matrix is this X matrix. So it is the matrix of your actual data. So if you were to go and if these were wants more children, this would be a column of zeros and ones corresponding to wants more children. It's really not magic. It's a matrix like you could make in Excel with a column of ones for your intercept and a column of your predictor variables here. And that's all that design matrix would be. But the key thing about it is that it defines what your coefficients are for. So it's telling you here that I need to fit a beta 0. That's what I'm going to multiply by this column of ones. And I need to fit a beta 1. That is what I'm going to multiply by this column of data. So the way you write down your design matrix defines what coefficients are going to be fitted. What would happen? So before, I think we were fitting wants more children equals no was the reference category and yes was the comparison group. So the ones where they did not want more children, these were zeros, and the other ones were ones. What if I coded that the other way in my design matrix here? We're doing this by design matrix now. If I coded this, so we have the alternate reference category. It's going to affect this beta 1, right? Because you're going to have to multiply something different to get these same y's. So the point here is that the way you code your design matrix controls the coefficients that will get fitted. And in that example, switching your zeros and ones will switch the sign of your beta 1. Because instead of adding your beta 1 every time there's a 1, it's the other ones that are going to have ones, and we're going to subtract them. Does this help demystify and either introduce or demystify, depending on whether you've heard it before? Who has heard of a design matrix before? Okay, if you don't use it in this course, you'll probably have to use it in EPI. You do use design matrices to define your models. I think you will. So I don't want it to sound like an abstract piece of linear algebra. I want you to understand that the design matrix is just your data. It's just a formalization of how you code your data. And when you write out a model formula in R, what happens is behind the scenes, without you ever having to think about it, it's encoding a design matrix for you. So in fact, your routine is using a design matrix, but one that's been created for you using some default options. So here's a simple example. I'm creating 2 groups. It's a factor with a vector 1, 1, 2, 2. And I'm using this function model.matrix to form a model matrix from that data using a model where something is described, a response variable is described by group. So the two things that are going into this are what are the actual data and what is the model. Right? So you have your data and your model, and those motivate what your design matrix is. And it's also called the model matrix, as you can see by this here. And look what it's done. It's produced exactly what I talked about on the last page. We've got one column that's all ones, and it's labeled that intercept. And we have another column that's called group 2, and that is now coded as zeros and ones. So even though our original data are 1, 1, 2, 2, or it could be cats and dogs, it could be anything, it's getting coded into a dummy variable here with a reference group, which was 1, and a comparison group, which was 2. Yep?
How does non-binary data work in this? How does it determine?
Good question. Well, what happens with non-binary data? You mean like categorical or numeric?
Numeric.
Well, I have
Or
an example.
categorical, really any. I mean, numeric data, because you don't have you don't have a reference group for that.
That's right. Well, check this out. I made group in the same way, but I didn't call factor.
Okay.
So, well, actually, I've got our studio open here. So, group. So it turned out a little bit different this time. What was class? Group. It's numeric now instead of a factor. So what happened is it just used the actual values. It didn't recode them as dummy values here. If I had done group C 0.5, 1, 1.5, 2, it's just putting them directly there. So that is one difference, and the other one was back. Oops. Okay. So with the factor, there was this extra stuff written down here that's kind of just an annotation that these represent contrasts rather than original actual data, and the fact that these didn't get messed with with the numeric variable. It was just the numeric variable preserved. So that's an important distinction, and I put this up right away to tell you, or to show you how things change if you have something like integers that are supposed to be a categorical variable, but you instead just leave them as numeric. In this case, your coefficient for group is going to be the same because you only have 2 numeric values and the difference between them is 1. So you would actually get the same coefficient here. But what about in this case? So look at this. I created a factor with 3 levels, 1, 2, and 3, and it has actually automatically for me created dummy variables for group 2 and group 3. So, and you can see how the matrix multiplication here would work. It's saying that for group 1, that is the reference group, all we're going to do is take the intercept. And the intercept is the prediction for group 1 because it's our reference group. For group 2, it's going to be the intercept plus this, because I'm going to be multiplying this. We have 5 observations here, and we will have a beta 1, we'll have beta 0, and the group fact 2 and the group fact 3 coefficients. So for the group 1, it's intercept and the other 2 coefficients get multiplied by 0, so they don't contribute. Person number 3 here was in group 2, so they'll get intercept and this coefficient will get multiplied by 1, but the other one will get multiplied by 0. And for this one person in group 3, they'll get the intercept, everyone does. Whatever that group 2 coefficient is, it gets multiplied by 0, and the group 3 coefficient gets multiplied by 1. So you can see here how for one given set of data, there are different ways that you could write out a model matrix. Here it's written out with group 1 being the reference group, but if you decided group 2 is going to be the reference group, you'd have a different model matrix. And we could do that. I use relevel function here to set the reference group to 3. And now you see there are columns for group 1 and group 2, but not for group 3. In the multivariate case, so here I've got an age group and wants more, but I've just made up some data as factors and made a model matrix. I have one column here corresponding to age group 2 and one corresponding to wants more, yes. So in this case, person number 1 is in age group 1 and wants more children. So for that group, coefficient wants more children. So it'll be the intercept plus the coefficient for wants more children. For person 5, you're going to get the intercept plus the coefficient for age group 2 plus the coefficient for wants more children. Yeah, so this is, each row is an observation, and this is just telling you what to multiply each of your coefficients by before you add them together. So your reference group will have a well, in fact, we have the way this design worked out here. Oh yeah, there are persons 3 and 4 are in the reference group for both variables. So they get the intercept, but the other 2 coefficients are multiplied by 0. So these 2 are a reference group in that they're age group 1 and do not want more children.
So you have to use the 0, 1 coding, or if it's like something like age, where when you have that table that we saw before showing the estimates,
yeah,
that's accounting for a 1-year increase usually, right? Right. So if it's 0.5, that's okay, because it's 0.5 times that, so it'll still be a true representation of.
Yeah, if we had actual age and you were going to fit a linear coefficient to it, you would just put those ages in a column and then whatever the coefficient for age is, it would get multiplied by this column and then added up. So that a 1-year increase in age would, this would be the age would be a one value of the coefficient added. If there is an interaction term, here we're just adding another coefficient or another column to the design matrix. So in all of the, and just like when we wrote it out in the formula, it's just a product of these two. So when there's a 0 and a 1, 0 times 1 is 0. Only when we have a 1 and a 1 is the interaction term 1. So remember, these are original data. These are your x's. This row 5 is a person who is in age group 2 and who wants more children. And therefore, they will have the interaction between age group 2 and wants more children contributing to their expected value. So just going back to this interaction term that we fit here with the contraceptive use group with age and wanting more children. Let's see, so our question here is the effect of wanting more children for 40 to 49-year-olds. Is the effect of wanting more children different for 40 to 49-year-olds than it is for the under 25 group? And that is answered by this, let's see, where is it? This interaction term here, which we can interpret as the effect of being in this age group as changed by, as modified by wanting more children. But what if one of the key things about design matrices is that they let you make any comparisons you want. So you can write out a design matrix that has potentially not the same reference group for all of the comparisons, that has 40 to 49-year-olds versus 30 to 39-year-olds. And maybe another comparison that is 30 to 39-year-olds versus the 25 to 29-year-olds. So you can have any sort of mixture of these coefficients that you want directly in your model. And there are a lot of ways to do this. I give an example here just from this multcomp package that allows you to define a contrast matrix in terms of the coefficients from an already fitted model. So from the model that I fitted on the page before, I just printed out the names of the coefficients. These are the rows that we had there. And then I want to ask this question about comparing the interaction term between the 40 to 49-year-old group to the 30 to 39-year-old group. And it's gone ahead and created a new design matrix for this and given me a direct estimate, standard error, and p-value for this group. So there are actually a bunch of different ways that you can create flexible design matrices. A package like multcomp is a handy way to do it, but you could also just do it in a spreadsheet.
Can you just explain what's happening in the first row with the -1 and 1? And how
Yeah.
that relates to them?
So what this is, the -1 and 1 here. Here, I'm going to go ahead and and show this. So this is just a one-row matrix with the 7th and 8th columns being -1 and 1. And if I look at this, these correspond to the 7th and 8th coefficients, and that means take this coefficient minus this coefficient. So if I just wanted like the difference in these two coefficients, I could tell that from here just by subtracting them. It's about 0.26 or minus 0.26, 0.27. But here I'm getting not only the estimate, but the significance test for it as well. So this -1 and 1 is corresponding to a difference between two of the coefficients.
So is the idea there with the -1 that you're comparing because it's the interaction terms, or comparing within the interaction terms?
It's comparing the effect of age on wanting, or the modification of wanting more children on these two age groups. So in fact, the other part of this matrix here is that this is one row. If you put multiple rows, you could make multiple comparisons here. So a second row, you could say I want the difference between this the 40 to 49 interaction coefficient and the 25 to 29 interaction coefficient.
So essentially, all of the ones that you're not interested in, you put their position as 0.
Or
in that line.
right,
Yeah.
right. So this -1 and 1 is defining a contrast. It's saying I want to first I want to know the difference in these two coefficients, and I actually want to see the results of the fitted model for that difference. If I had fitted a model that directly had a coefficient comparing 40 to 49-year-olds who want more children to 39-year-olds who want more children.
What's the last one in that row? The one inside the last parentheses?
The last what?
That last one in the top row?
The last one. This?
Yeah.
Oh, that's the number of rows.
Oh.
Yeah. So that's like.
So in this analysis, you're not doing the same thing as you're doing in the above analyses, right? Because in the above analyses, you want them all set up as 1s or 0s, or the continuous variable of age, in order that you can multiply each coefficient, or so you can basically, yeah, you can multiply each stated coefficient to be either not there or there, or to be 0 or 1. Whereas with the -1, you're asking it, you're specifying that you want to compare the difference within those interactions.
Yeah. So in this model, I'm fitting coefficients to a number of different comparisons, like the difference in log odds for a number of groups, or the difference in coefficients between two groups for the interactions.
Okay, so that's the difference right there. So can you say that again, like that exact thing? Just like crystallize it.
So this model is telling me the difference in log odds between some pre-specified groups. The interaction term's a little more different. It's like the difference in coefficients. By using a custom design matrix, instead of getting this particular group, I can take this this regression and get the same kind of results for any arbitrary set of contrasts that I want. And this is a pretty simple model with only 2 variables, but if you had like 5 variables, that might be really valuable. There might be specific hypotheses that you have that you want to know. I want to know, okay, is there a difference between these groups? Is there a difference between these groups? And rather than going and refitting another model and going through that all of for every one of these different hypotheses that you have, you can specify a custom model matrix that just fits coefficients to what you're interested in and only what you're interested in. Any more questions before I'll give you a 5-minute break, and then we'll spend some time on the lab exercises. Oh, let's talk about, maybe before the break, let's talk about your assignment. Let's see. Has anyone looked at it yet? All right, so it's an assignment on logistic regression. And there's a published paper that did a logistic regression. Very nice. They did, they wanted to do causal inference on a number of factors that might predict the completion of a complete set of Gardasil vaccinations against HPV for young women. And so the response variable is whether or not they completed this series of vaccinations, and they have a number of predictors like whether they're in an urban or a suburban location, the type of insurance they have, and a few other things. So I took this, they have a structured abstract. I took this, this bit right out of the abstract, their results. And I'm asking you, these are also in a table, table 2 and 3, which provide a univariate analysis and a multivariate analysis of their data. And I'm asking you to attempt to reproduce those 2 tables. So take their data set, do your univariate and your multivariate regression, and compare what you get to what they got. And write a little report about it. Doesn't have to be a long report, but it should have these sections: an introduction, methods, results, and discussion. So your introduction, just a little bit about, yep.
Do we have to cite other papers when we're writing the row or discussion section?
You can cite a couple papers that they cited. You don't need to go outside of what they did. But yeah, the introduction, what I like to see is just very briefly, this is the context and this is the assignment, just to show that you know what it's about and what the assignment is. Yep.
How many pages?
I have no requirements on page limits. In fact, I hate it when a page requirement is too long and everybody just tries to expand it and fill in the space. So as long as it takes, and you know, I've seen a wide variety of them before. I've seen excellent assignments that that were only a little over 2 pages long. I mean, it's hard to fit it in too much less than that because you'll have a table or a couple of tables in there too. But it doesn't have to be really long. The key, like with methods, I like to see concise and complete methods. Like I don't like to see really verbose, unnecessary methods, but I like to see everything that's required in there. And that can be, if you know, it depends on how concise a writer you are. That can be pretty short. Would you all be happy if I posted an example?
Yes.
Okay, if you're really nice to me, I will post an example. What's that? Yeah. No, I was gonna post one anyways after you handed yours in, so you could see, but I'm feeling nice, and that way, the only reason that I would be hesitant to post the example is that there are actually some problems in this paper, and I feel like you gain some grit by trying to figure out what they did and why they got the results they did, because their methods are not complete. And one of the things that I hope you all will get out of this course is realizing how to write a complete methods section. It is like really surprising how often method sections are incomplete in the literature, and unless you've tried this yourself, to go to someone else's methods and do what they did and find that you don't know what they did, then you probably become one of those people who doesn't know how to write a complete methods section. But I'll do it. The plus side is, you know, I want you all to know what's expected of you and not to freak out. You know, this is not a term paper. It's not a dissertation. Like it's just to communicate your results to people. So, and that is one of a couple of the program competencies that you're supposed to get through this course are communication of statistical and epidemiological results to a broad audience. So this is the kind of thing that you would present to your collaborators on a project, and that could go into a paper. It's not like a paper, but this is the basis for a paper. Yeah.
So especially meaning that you're saying that the authors didn't necessarily get their methods or results exactly right. What is the goal in terms of the results that we're trying to get? Should they be similar, dissimilar?
In this case, it is possible to reproduce their results once you figure out what they did about the missing data, because they didn't mention how they dealt with missing data. So the ideal thing in this case would be your results. You can show that you reproduce their results and say how you did it. And in your discussion, you would say what the challenges were in figuring out what they did.
And if we get something like way off?
So, you know, if I weren't, you know, showing you the answer, you tried it, you got something different, but what you did was correct, and you described what you did, and you said that it differed from what they got, you would still get full marks for that, because you're doing a correct analysis, and you're describing your results in the results section, and you're discussing how they differ from the published paper. That's fine, but the ideal thing is that you do figure out what they did and are able to discuss what is required to reproduce their results and what was missing from the original paper.
Forensic work.
Yeah, it is a little bit of forensic work. I mean, ideally it should not be, because their methods should just tell you exactly what you have to do. But it doesn't always work out that way. So other things to note about this. So we have no class next week. It's a holiday next Wednesday. in 2 weeks, we'll be back here, and about a quarter of you will present your results, but all of you will submit your preliminary analyses. So for 2 weeks from now, I will put up an assignment, and a preliminary analysis is due from everyone. I don't actually grade these preliminary analyses. They will contribute towards your participation score, so you need to do them if you want a full participation grade, which is 20% of your grade in this course, so do it. The rubric there is basically, where is it? Here. It's also in your grade for this course. So 0 points for no initial submission, 1 point for a partial attempt but missing at least part of it, and 2 points is an honest attempt at the whole assignment. So it doesn't have to be correct. It doesn't have to be, you don't have to finish it. You just have to have tried it. So the idea is that when a quarter of you get up here and present some results, everyone has tried it, and we can have a good discussion about it. The presentations are going to be pretty short. They'll be under 10 minutes each, I think closer to 5. I have to calculate again. I think there are close to 35 of you in here. A quarter of that is 9. So actually, no, it can be 10 minutes or even a little bit over 10 minutes. But as a presenter, ideally, what you should have is a slide deck, and you have these sections that basically in your slide again have an introduction slide, have a bit about your methods, what you did, your results, and some conclusions from what you did. And that will help everyone to get a pretty good idea of what's going on. And then 1 week after that, everyone's final reports are due. And that's how all 4 of these will work. Sound reasonable? All right. It is a different kind of assignment than you've had in any of your classes up to now, but it's a realistic assignment. These are real data sets, and you can see some of the real thrills and spills of data analysis in the real world. Okay, let's have that 5-minute break, and then we'll have like 20 minutes left.
Next week? Not necessarily.
Well, actually, I have a question regarding the code. You can, for the assignment.
Yeah.
You said for like, so you said you don't know what, yeah, you don't do that. So how does that? No.
Well, what I'm saying is that I can't really support that.
Oh,
You can do it, and that's fine. It's just I can't.
I'm sorry. Right, but you can still read over the yeah, the general, just do it.
Yeah. I mean, I'll still read it, but like the report itself, like the coding, all I need to see is that you have a program that runs and does everything that you did, or everything that you're reporting in your report. But the report itself is just results.
Okay.
Yeah.
So is the code essentially what I'm looking for? An appendix?
Yeah.
Okay.
Normally your code would be a separate file. If you're using R, ideally what you will do is have a source file that's an R Markdown file, and then a report that is produced by that. But it could also be like a Word document that you just write your results into in a program that you run to do your analysis. That goes into the, where was it? The reproducible analysis.
You have questions to ask? Sure.
part of
Are
the
there any
rubric
questions, or if there's
that I can get your results again by running your program.
questions about that too.
Did those start already?
No.
When did they start?
Set it up tomorrow sometime, so.
But for tomorrow?
But I think
The free session.
the free sessions, yeah, you can watch.
Sorry.
Where you get the free, watch free sessions from?
So.
Yeah, definitely.
So it's just like. We don't all have to watch it together.
But they're gonna be posting it one.
So it's like. It's for Sarah. And then put it together. If you have questions, videos or
But to follow along these courses, you have to have heart.
you could just watch the video.
But I mean, would it work with the virtual classes? Or is that different? Do we have virtual admissions already started?
Hold on.
Yeah. You do it all. Where get information about So what do you need to do? You put your email. Oh, okay.
And then, so like, they have one file last minute, eventually.
What a chance.
So those are now.
Yeah.
And this class tomorrow is basically questions.
If you have questions about that, questions about anything.
Yeah, I don't even have questions right now.
I heard it's a good show.
I'm sure there will be a lot of questions, but right now.
Now that.
Just, even if it's just journal.
So, but for tomorrow, it's just questions and answers. It's not like the lecture.
I'll work through some labs.
But we can watch it, we don't have to have questions, right? So it's just data, data that column.
Yeah, it's dead.
Maybe what I will do is I'll sit here and work on these problems up on here so you can kind of watch what I'm doing while you're working on it yourself. And Lucas will be going around and put up your question, your hand, he'll come by and answer your question, or maybe I will too.
This is usually working through this on R.
Mm-hmm.
R Studio.
I'm going to start it by doing create a new R Markdown.
This is R Markdown.
So R Markdown, when you do new R Markdown, it gives you a template like this. And it is a so-called literate programming document. It contains code and formatting and text all in one thing. The key parts, there's this top matter. Then there are so-called code chunks, which have these 3 backticks and some options and curly braces, and then our code inside them. And then everywhere outside those is not going to be interpreted by R. It's just going to show up for the benefit of human readers.
Is there an alternative we could use if our current version of Studio doesn't support that? I get a message if I want to do it that says you need to like update your versions of some of the add-on packages. So would I be able to do it using one of the other existing, like our notebook or our script?
I mean, you can have just an R script, but that's just a program that doesn't produce the rest of this. Like, let's say I will.
It only takes like a minute to load all those packages.
Oh, really?
Yeah, yeah, you should do it. So just the example here, I just clicked on knit HTML, and it produced this for me, so you can see what happens. So this text that was here, there was, let's compare. The two hashtags, that's a header. One hashtag is a heading 1, 2 is a heading 2. Then there's some text here. They give you a link to where you can get some help on text formatting stuff. Like if there are 2 asterisks, it's like a wiki. Put stuff in boldface. Yep.
Can I ask you a very silly question? How do I save everything I have done in the console into a file? Or that's all automatically set in like a temporary folder?
Normally, I do not save what is in the console. This is only for like interactive use. But if you did want to save it, you would go to this history. Yeah, you could. Let's see. I'll try control. Well, this has only the commands. If you actually wanted everything that was in here, I think you click here and just highlight stuff and copy it somewhere else. But this is kind of like logging output. So normally the only thing that you really want to save is this program or this markdown file up here and the product of it. So I got, just from this, you see there's this plot pressure, this summary cars. These turned into, they actually got evaluated and produced results. One kind of cool thing is instead of HTML, I could have chosen Word, and I get a Word file with this in it. It's kind of neat, right?
That's awesome.
Yeah. Or a PDF. PDF can cause problems in that you need to install a so-called tech installation that's not on this computer. So, but I can get, without any further installations, the HTML and the Word. So the first thing I'm going to do here is I'm going to delete all this stuff. And I'm going to copy this. Okay. So I haven't actually done any analysis yet, but I've created a shell of a shell of my document. I need to remind myself of how to load the data set. Okay, there we go. I used a Control-Alt-I shortcut instead of doing code. Where is it?
Where was that line of syntax again from last week where you could load the data easily? That line of syntax right there, yeah.
I got that from looking at the class BIOS 621 session3.rmd. I copied it out of there. What was that?
Down on row 140.
What's that?
Way down on row 140.
Oh, great, thank you. Yeah, I see 141.
I use the shortcut so much that I don't even remember where the menu option is. Oh, that's the very first one. Insert chunk is what you do, or Control-Alt-I, or it's Command Control-I on a Mac to insert a chunk of code, which looks like this. Fortunately, I do all of my lectures using R Markdown, so you've got plenty of examples in there of using it.
So you have to put the R in the really brackets to get it to read it as code.
Right. So if, let's say I put this once here inside the, once inside and once outside. Here it's just regular text. Here it's actual executed code. It's only executed if it's inside there. Yeah.
I tried to badly put it in, and it says error, attempt to use your own variable name.
Okay, well let's try this here.
I mean, like, it loaded in, but it's still giving me error message.
So I did Control-Enter to run this queues. What happens if you go down to the console and type queues? Does it look like this?
Yeah, I think that's. Yep.
So what did you do that gave you an error?
I don't know.
You want to go take a look, Lucas?
It says, I think it was like the summary function. Oh yeah, it's summary queue. That's where the error came. It summarized it, but some of it, but then it still gave me error message.
What happens if you just type queues?
It comes up exactly. It goes here.
If you do summary queues, you don't get this.
I do, and then I get an error message.
Let me take a look.
No, it works.
Fraction of women using birth control for each age group. Okay.
Get your phone. I changed my phone. I know. We have more time. Facebook. Yeah.
And then the small things that like they committed that don't have.
I just want to see impact without it. I still have to go. Yeah, I was gonna stay after the class. I just have to everything first.
I know that. So pretty much that's about penny.
I got you here. Okay, I'm messenger. Oh yeah, just get. So what day is it? The Tuesday, Wednesday, they're closed. And no, it's Jewish holiday. Are they gonna be open?
That's what I'm asking. She was excited. So. When you start
It's a lab.
What's up? No, you don't have to submit the lab.
No, I mean, it's online.
You don't know that you cannot
There are no exams. No, they're, yeah, they're for assignments. Yeah. Yeah.
Yeah, there's like learning the language and then learning.
Yeah, that's true. Oh, you finished the first one? Okay. Okay. How did you like it, the first one?
It was helpful. It was helpful. Yeah, definitely. I thought it was helpful for like background support for learning the language to be able to hopefully like do these things more quickly. Like, so yeah, I mean, I'd like to really look at all of those.
Yeah. It will only help you.
And make a new call.
Yeah, and then there's SAS also, right?
No, there's no data camp for SAS.
I'm gonna be texting.
They're textbooks.
Right, and that's what we're doing. I think we're doing more SAS.
Cues typed into the mutate.
Typed into mutate? Sure, like,
Yeah. And then delete it.
I need the,
We don't
need it, just,
So what's happening there? First. to use it so much that I gotta make me explain it. With this pipe operator, Q's becomes the first argument of mutate.
What are the percent signs there for?
That's a pipe operator. Percent, right arrow, percent. The first thing becomes the first thing of the next thing. So the input of one line becomes the input of the next line. The output of that line becomes the input of the next line. And so you're chaining these steps together. And it just goes over here. And it makes more sense. So you start out with your data set. You calculate a new variable. And you're going to group it into categories by age. And you're going to do a summary of that by taking the mean of the.
I don't think you don't need to mutate, you just use one variable and just using by not using the collective proportion. Why do you
mutate is our main data structure in R is a data frame. And you could do it. You could just do it and it would be there, but it would kind of so additional. If you keep it, you can do these other things like you can.
Isn't this,
For your good eyes,
yeah.
because that's not a line of our code. Try running that one. This is like our markdown syntax. The R code is held inside of it. So it was pretending like that was our code. Right. So just go there and do like Control Enter.
Okay, so. Because you never whatever it was with the echo equals false.
Mhm.
Again, I should have highlighted questions.
Right.
So you just, if you're just on, you're at the beginning for Y, you can do control. Okay, but if I'm on that previous line.
Right. Yeah, it's not a harmful error. I mean, it's just saying I have no idea what you're talking about here.
But that is necessary, that's.
It's necessary when you're code equipping. That's what tells it that this is our code inside here, and what's outside there is not our code.
So,
Well, plus this data set is one line for observation, which is further encouraging. You know, it's really hard to try to do the column
When you do this, you'll see this code during your output. If you put comment echo equals false, you'll no longer see this code, but you'll see the results of Yeah, exactly. As an aside, if you use the notebook output, it's not so necessary because all of the chunks can be hidden or shown with the notebook output. If you do like,
This other one?
yeah, with that one. I don't know, I don't use it myself, but
So we copied the
it
list.
produces an HTML file where you can expand or collapse all of the code sections, and it has a little button that allows you to download the original R markdown file, which is kind of cool.
You're supposed to create swing group. That's after this.
It is super handy. Another great feature of it is, I mean, there are a ton of chunk options. You can put comma cache equals true, or put uppercase offline cache equals true, and it'll cache the results of all of
So
them.
we need to.
So if you have
we
like
need to,
a simulation that takes an hour to run, it'll take an hour to run the first time you knit, and then it will be instant the next time because it'll just load the results off of disk.
So I don't know how to do that in this case here.
Yeah.
it does actually have a note there, and that's a very nice way to do it. So,
Sorry, for the first lab.
The codes for the first lab.
But
Oh,
the library.
I did already.
The library.
Yeah, it's there. Look.
works,
Oh wait. Oh, sorry. For the first lab. No, that I did for
packages.
this lab. Maybe I forgot for the first lab.
Right, the first lab was, I think you mentioned we were going to just.
Yeah, Pokemon. Wait a minute. Let's see. Oh, for the last one, it's the same thing. I just lab 2, 3. Yeah, like if
So then we
this
just, how can we know if that's what we're supposed to do?
2-3 lab exercises. These are the these are solutions.
Okay, so.
Yeah. Yeah.
Good to learn. I think we should spend a little more time on the labs.
Yeah.
Good night. If you guys want to answer instructions tomorrow, I'll do the labs.
Yes.
Yeah, I have to take it online. I'm not going to be here.
I couldn't find it. So
So it's gonna be online.
Okay.
Okay.
I sent out a.
Yeah.
Is this and a little quick around the University of Pacific quick sheet? Is that there?
They're even check this out. Go to this.
Yes.
So that's what that stands for, DY.
Oh. Yes.
That's data.
Okay. Could you guys bring in the laptops?
Oh, yeah.
They need to be taken to the next class. But there is a computer lab right out here if you need to still use a computer. It's okay.
Like saving this all down?
Use the system. Yes, it is good if you have like non-English characters and stuff.
Okay, thanks.
Yeah. Yeah, it's fine with me. I know nothing about data, so I can't help you, but yeah. Yeah. Yeah.
Yeah, I try to say
Well, I mean, if it's just results, you've got results from the from there, so you can kind of see if you're getting the same results. But yeah, no, you will not be penalized for using data.
maybe number 2 will be okay.
I don't think. No, I don't think it's close. I think so.
What time do you usually get?
5.
Okay, there's how I can do it with PowerPoint and
Something in.
good night. Okay.
Okay.
Great.
Good night.
There's
I'll see you next,
Okay, see you.
2 weeks.
2 weeks. Yeah.
Jen
Oh, that reminds me, I need to stop recording. Okay. What's that?